Hi everyone, and welcome to exercise 5 on page 65 of the workbook. And this problem is asking us to determine what non-zero values of k makes the function y equals e to the kt a solution to the differential equation y double prime minus y prime minus 6y equals 0. So the way that the question is worded suggests the fact that some values of k are going to make this function a solution while others aren't. And it's our job to figure out which values of k work. Okay? So let's remind ourselves what it means again for a function to be a solution to a differential equation. It just means that we'd like to be able to substitute e to the kt in for y and get a true statement out of our differential equation. That's exactly what we're going to do. Notice that when you look at that differential equation, there are a bunch of derivatives there, which means we're going to have to take some derivatives of the function y. Why don't we do that first, okay, before we go to the equation? So if we start with y equals e to the kt, what would the first derivative of that look like? Okay, well, take the derivative of e to the kt, you would get e to the kt times the derivative of kt. And since k is a constant, that just means we're going to get k times that. So we'll get k e to the kt. So there's y prime. What would y double prime look like? Okay, well now we're kind of starting from here, k e to the kt, and we're just going to do it again. Take one more derivative. Okay, well, we do that. K is a constant, and then we need to take the derivative of e to the kt, which again is e to the kt times k. So what ends up happening is that we've got two copies of k. Put those together and we'll get a k squared. Okay, so there's y, y prime, and y double prime. Okay, and now let's see if we can investigate the question of when do we get a solution to this differential equation. Okay, well, we would get a solution when substituting y equals e to the kt into this formula would make it a true statement. So let's do that. Everywhere we see a y, we'll put an e to the kt. Okay, and the question is, what values of k make that a true statement? We're trying to solve for k here. All right, well, you can see from this equation that we've got some derivatives to take. So starting with this first term here, that's asking us to take the second derivative of e to the kt. We actually did that here and got k squared e to the kt. Okay, so there's our first term. And then we come to the second one. That's just the first derivative of e to the kt. We did that calculation and got k e to the kt. Okay, and then finally for the third term, nothing to really do there. That's just 6e to the kt. Okay, so we've got an equation to solve that looks like that. And do you notice anything algebraic that we could do in that equation? I noticed that there's an e to the kt that's kind of common to all three of those terms, so why don't we factor that out? Okay, so by factoring, that kind of reduces this problem to two different possibilities. So for this equation to be true, either e to the kt is 0 or k squared minus k minus 6 is 0. Sort of breaks our equation into two separate sub-equations. And the thing about this first piece here, e to the kt equals 0, if you think back to algebra for a minute, it's not possible to solve that equation because e is a positive number, and no matter what power you raise a positive number to, you're never going to get 0. Okay, so this has no solution, which means that we don't even need to worry about the first part, the e to the kt equals 0. It really comes down to what's going on over here. Okay, and you might notice that we can factor k squared minus k minus 6. That factors as, let's see, k minus 3, k plus 2, I believe. And now we can kind of see the two possibilities. Either k equals 3 or k equals negative 2. Okay, those are our two solutions. And that answers the question. We know that y equals e to the kt is going to be a solution for exactly those two values of k.